Okay, week 8, video 6, design 2. So this is continuing the story of design, and in the end of the last video I talked about the idea of top-down design. And what I want to do in this video is give you an idea of how this might proceed in a somewhat idealized world. So the problem that we're faced with is, how do I write a program to play noughts and crosses, also known as tic-tac-toe? There's a link here if you don't know the game. And it's going to be a human versus a computer. So starting with complete ignorance, what do? Remember, if you didn't already know, that noughts and crosses is played on this 3x3 sort of grid, in which one player puts an X, the next player puts an O, first player puts an X, and so on until somebody either has 3 in a row or the board's full. We call the latter a draw. So even if you don't know anything about the process, and let's face it, you're always exploring space here, you know you're going to do something like this. You're going to have to make a board. That's the first thing you do, draw the lines or equivalent in a computer. Determine if the user, the user being the human, do they wish to be O or X, and then you play the game until you're done, and then you state the outcome. Well, it turns out we can actually write that much in Python. We don't necessarily know where we're going, but it comes out looking like this. We've got a main function which plays a game, and it says board is a new board. We don't know what it does, but I'm going to create one, right? We say the human player is the value from the function get O or X, again, just a piece of code we have to write, and then we play the game. This is kind of a biggie, and we print the result. If we want to make this code actually run, and it's kind of important when you're developing software that you keep being able to run code, otherwise you run out of steam. You need to keep reassuring yourself that what you're doing works. So here I've written in the 4 functions I needed with bodies of pass, which just means don't do anything. So this code works. Bingo, you see, it runs. It doesn't do much, but it's at least syntactically correct. So we can move on to the next phase. The next phase is, well, we've got one of these 4 functions. Which one are we going to work on? We're working top to bottom, remember. So functions 2 and 4 get O or X and print the result. Well, you could write those. They're kind of straightforward. This is just a simple input function. This one's printing something, you win, you lose, whatever. So those 2 are kind of easy. Let's focus on the interesting stuff, which is 1 and 3. How do you make a new board? What's the contents of this new board function? Now, there are actually several different things you could do, but I'm going to assume what we're going to do is, is this. That is, I'm going to represent a board as a list of 3 lists. This represents a row, first row, second row, third row. And each cell in the row, each square if you like, is either dot or X or O. Now, I've assumed a lot there. And of course there's other ways of doing things, and they lead to very different programs. I might have assumed, for example, that I'm going to represent the state of the game as 2 lists, one being the list of all the squares occupied by O's, and the other being the list of all the squares occupied by X's. They work, both representations work, but they lead to very, very different bits of code. And that's one of the issues with top-down design. You can make a design decision and then land up in a mess, possibly very much later. But that's true of all software design, so exploring the space is part of it. Okay, at this point, you probably should switch to a little bit of bottom-up design and try writing some low-level functions like display the board, make a move, just to make sure this representation is viable. I'm going to skip that. They're straightforward enough. Hopefully you could do those right now. You may even want to if you want a little bit of a break from a video. So the interesting stuff at this point is that line there. How do you play a game? Right. Well, again, using top-down design ideas, I don't know how to do it, but certainly I have to be in some sort of while loop. I can't be in a for loop. For loops are used if you know exactly how many times you're going to do something, and we don't know because somebody might win on their third move. So we're going to write it as while we're still playing. And in actual code, I've translated that into while not game over. Right, so just writing functions, assuming all the detail that's yet to be written is in the lower level functions. I've still got to write them. While not game over, you need the board parameter, because otherwise how would you know whether it's over or not? Display the board, play one turn, whose ever turn it is, and switch players. So O's turn, then X's turn, O's turn, then X's turn. So I've assumed the existence of some function other player, and I've written a function play one turn. What do I do next? Let's move right on to the more interesting stuff again. Play one turn. I want to write this one. Now, actually, I've cheated a bit here. This version says play one turn, takes the board and the player. So it should have looked like that. But what we find when we go to write that function is that we have a wee problem. And the problem we have, if I have it here, is that when I try to write play one turn with just those two parameters, I want to ask the question, if it's the human player, then we're going to call a function human move. Otherwise, we're going to call a function computer move. How do I do that? I can't with those two parameters. I know what the board is, I know who the player is, but I don't know whether the player is human or not. So I have to add a parameter. And this is the part of the process of being exploring a space and backing off when you've made a mistake. So I need to add an extra parameter, which is what you're seeing over here. And what you saw me having written in already, I need a human player in here. To pass that information in, play one turn, current player, human player. Then I can ask if the player is equal to the human player, then I'm going to do make human move, and I'm not going to type it all in, you can see it over here. Make human move, make computer move. How do we write make human move? Continuing the story. Well, we've essentially asked the user where they want to move. And if they come up with a bad answer, you can't move there, it's full or it's not even a legal square, we're going to ask them again. So we've got a piece of code which is very much like the sort of code you've been writing in 121. While they haven't made a valid choice, ask them for a location, and the location is valid only if it's an empty square they've chosen. If it's not a valid choice, you write an error message. And this is stuff for you to write. I'm not going to do that. All straightforward. How do we make a computer move? Sounds real hard, right? And it is if you want to do it properly. But there's a very easy way of making a computer move, and that is just to choose a random empty square. That's what we're going to do. We'll clean the code up and make it better later. Who knows? A random empty square will sometimes win. And how do we do that? Well, we make a list of the empty squares. We call a function which is in the module random. Feel free to go and explore that. You have to import random, or from random import random in range, and then it gives us a random number in the range 0 to the len of candidates -1, and we use that to pick the column in which we're going to play. So it actually turns out to be really easy to write a very poor function make computer move. How do you check if the game is over? Well, you check if it's a one game or it's a draw, and it's a draw if the board is full. And at this point, how do I check if the board is full? Let me see. It's full if there are no empty squares. But hey, I just wrote a function to find out the list of empty squares. Oh goody, I suddenly make a bit of a discovery. I can write the is full board as the len of empty squares of the board is 0. So it turns out nothing more to write, nothing much to write there. This is a bit harder. Is it a one game? And that's actually probably the trickiest piece of the code. I'm not going to go through that. It's more detail. What I want you to come away with is the idea of this, what in computer terms we call a tree structure, a top-down. Actually, it's not a tree, it's a graph because they join again. Okay, forget that. It's a graph which goes top to bottom. Top-level function main calls new board. Let's have a look. Main calls new board, get O or X, play game, and print result. Play game, in turn, calls game over, display, play one turn, other player, game over, display, and so on. This is called a call graph. It tells you what functions are called by each of the other functions in the whole game, in the whole program. So hopefully at this stage you can see that we're down to small enough bits that you could in principle yourselves put the program together. And in fact, if you want some entertaining recreation, I suggest you even go and give it a go, see how you get on, fill out all the missing bits using what we've given you here. So, excuse me, what I hoped you'd got from all this was that First of all, programming is not a formal process in which you just turn a handle and out come some programs. If it was, we programmers would be out of a job. It's a creative process. It involves exploring a space. I've been showing you a particular idea or ideal of top-down, but none of the methodologies that you can think of work in entirety perfectly the first time. They always involve exploration, backing up, whatever. Top-down, bottom-up, sideways, spiral, whatever. And there's experiment involved. So you should expect to make mistakes. Some people get very depressed. Oh, I can't get it right. Other programmers can write it better. No, everybody makes mistakes. I call them discoveries. They're not really mistakes. They're the fact that your knowledge is incomplete when you start, and incomplete knowledge will always lead to discoveries, as I prefer to call them. And the key aspect of all of this, the key components in design, are functions. They give you the divide and conquer, breaking it down one piece at a time. They give you the ability to test in small pieces, and perhaps possibly even more important, they give you confidence that as you proceed, you are getting somewhere. So that's all from this video. I hope you got the general idea of top-down design, keeping in mind this is an ideal, it's something to aim for. Don't expect it to work first time or even second time. Just something to practice with in your future programs. Thanks for watching. Bye.